Let's give a formal definition of current flowing through a wire. This shows a wire, a conducting wire. We imagined a surface that crosses that wire and divides it into two parts. And through that surface, we choose a direction. So here it is chosen from left to right. So this direction is going to be important. So we define the current that passes through that surface as the charge that crosses the surface in the direction of the arrow divided by the time interval. You can also define it like this. You can write down the definition like that. So you just think of all the parts of the wire on the right side as some big system and use QR to denote the charge on that system. So in that case, that current would be change in that charge divided by the change in time. And for very short time intervals, or if you take the limit, you can also express it like the derivative. But please keep in mind that it's not really a derivative in here. By this expression, we always mean that expression. So there's some kind of an operational definition in here. So you wait for a certain time and you just measure the amount of the charge that crosses a given surface, and then this is just a ratio. It's not a derivative. And the main reason is that, of course, this QR is not really well defined because usually this wire just continues around in space and then it's connected to the left side. So there is no unambiguous way of defining that QR in here. But operationally, the amount of the charge that crosses that surface through that wire, this is well defined. Okay. So let's talk about the units quickly. So in SI, the unit of current is coulombs per second. We just call it as ampere and show it with the capital A symbol. So we know that in SI, ampere is the base unit, and coulomb, which is basically ampere times second, is a derived unit. Okay, there's some kind of a detail about this. There's a reason why we define it like that, but we are going to see this later. Let me also note this thing. Since the charge can be positive or negative, so by choosing the direction of the arrow, we somehow set some kind of a direction. But in that case, this charge can be positive or negative. So as a result, with this definition, this current can be a quantity which is either positive or negative. So both values are possible. So let's also talk about this thing, because depending on the choice of the arrow, the current can have a different sign. So as a result, let's say that I'm measuring the current at that location. So again, I have a surface, an imagined surface that crosses the wire, that cuts the wire into two. So I'm talking about the current at that point. Okay. If I choose the direction of the arrow towards right, I'm going to get a current value. If I choose the arrow in a different direction, I'm going to get a different current value. And because of these relationships of the directions, it's kind of obvious that this current measured using the other arrow is the negative of the other current. So if you want, I can actually give this as a numerical example like that. So a current which is to the right, which is equal to, let's say, plus 2 amperes, is the same thing as a current flowing towards left with a value of minus 2 amperes. All right, so if we just accept this definition, in that case, we will be very comfortable later on, because usually we choose the arrow before computing the value of the current. So as a result, it may turn out that the value of the current with our chosen direction might be negative or positive. Okay, so if we accept that the current can be negative, in that case, we don't have to think deeply about the choice of these directions. We just somehow choose a direction and accept all consequences that come with it.